Hey everyone. In this last video, I'm going to talk about basic concepts in linear algebra. And linear algebra is important as soon as we start talking about linear regression on OLS. We will show a lot of results and properties of the OLS estimator using linear algebra. So it's really important that we have kind of a grasp of the underlying ideas and concepts in matrix algebra or linear algebra. So in general, linear algebra describes kind of working with vectors and matrices as objects and using kind of mathematical transformations on these vectors and matrices. So what is a vector? A vector is defined as, or a vector in n space is defined as an ordered list of n numbers, okay? So, and these numbers can be represented as either a row vector or a column vector. So in this case, we have a row vector v that has n individual elements v1 through vn. We can also think of a vector as defining a point in an n-dimensional space. So usually that would be Rn, so real numbers with n dimensions, and each element of the vector defines the coordinate of the point in a particular direction, right? So, you know, the simplest way to think about this would be in a two-dimensional space where the first element is the position on the x-axis and the second element is the position on the y-axis, and the vector itself would then be the vector from the origin, so from 0, 0 to whatever point in this coordinate space x, y you would have, okay? When we have vectors, we can add them together, vector addition and subtraction. For two vectors, u and v, in order to be able to add or subtract them from each other, they have to have the same length, okay? Since vector addition and vector subtraction is element-based addition and subtraction. So if we add two vectors together, we just, for the first element, we add the first element of vector u and the first element of vector v, second element same, and so on. And so, of course, in order for that to work, we need both vectors to have the same number of elements. Last, for vectors, if we have a scalar, so just a single number, which we call, do you notice C here for now? If we have the product of a scalar, so some constant, and a vector v, then this vector, the result is basically C times each individual element. So the result will still be a vector, but each individual element of that vector will be multiplied by C. And we kind of intuitively, all these kind of rules make sense, and we've already seen them as we were working in R with vectors, but it's important to kind of like have a good grasp of these underlying concepts. An additional concept that we might encounter is the vector inner product. The vector inner product, or sometimes also called the dot product or scalar product of two vectors u and v, is defined, again, if and only if both vectors have the same number of elements, so they have to have the same number of elements. And then if they do, and we compute the vector inner product, what this means is we multiply each element, at each position we multiply the element of vector 1 times the element of vector 2. So here u1 times v1, and then we add all those products together. So u1 times v1 plus u2 times v2, and so on up to un times vn. And for this product, one thing that is important is that if this product is equal to 0, what this implies is that both vectors are orthogonal. Okay, so so the degree, the angle between those two vectors is 90 degrees. So we could think of this as, for example, if you have, you know, in this two-dimensional space, one vector that is just 0, 1, and the other vector is 5, 0, then they're kind of both on the x-axis and the y-axis, and they're of course orthogonal or perpendicular, and if we kind of multiply the elements and add them together, we end up with 0. Okay. Another important concept is the vector norm. The norm of a vector is a measure of its length. There are a lot of different ways to calculate the norm, but the most common one is the Euclidean norm, which ultimately corresponds to our usual conception of kind of distance in a three-dimensional space. If you remember computing the length of in a triangle, where you know kind of the two orthogonal sides, we can compute the length kind of the third side by computing the norm as basically the square root of the individual elements, or the square root of the vector norm. So ultimately, the square root of v1 times v1 plus v2 times v2, and so on. Okay. Another important concept is linear independence. In order to understand what we mean by linear independence, we first have to talk about linear combinations of vectors. So a vector u is called the linear combination of the vectors v1, v2 through vk if it can be basically described as a sum of the vectors times times a set of constants c1 through ck. Okay. So what does this mean? That means, just to give you an example, the vector 9, 13, and 9, 13, 17, so a three-element vector, is a linear combination of the following three vectors: 1, 2, 3, 2, 3, 4, and 3, 4, 5. And the reason for that is that this original vector 9, 13, 17 can be described as 2 times, or is equal to 2 times the first vector 1, 2, 3, plus minus 1 times the second vector 2, 3, 4, plus 3 times the third vector 3, 4, 5. And if you go through the math in this by multiplying 2 times the vector, minus 1 times the vector, and 3 times the vector, and then adding all elements, you'll see that you'll get to 9, 13, 17. So in other words, the original vector is a linear combination of the remaining three vectors. What linear independence now means is that a set of vectors is linearly independent if the only solution to this equation is equal to 0, which means the only solution to the equation c1 times v1 plus c2 times v2 and so on up to ck times vk is equal to 0, is that all scalars, so all constants c1, c2 up to ck, is equal to 0. If another solution exists, then the set of vectors is linearly dependent. So in other words, if another solution exists, then one of the vectors v1, v2 up to vk can be described as a linear combination of the remaining vectors. Okay. In general, a set of S vectors is linearly dependent if and only if at least one of the vectors S can be written as a linear combination of the other vectors in S. And this notion of linear independence, and to what extent one vector can be described as a combination of the other vectors, is ultimately really important when we talk about inverses of matrices. In general, linear independence is only defined for sets of vectors with the same number of elements. Any linearly independent set of vectors in n space also contains at most n vectors. So as soon as you have more vectors than you have elements in the vector, then at minimum one of them has to be a linear combination of the other ones. Now, moving beyond vectors towards matrices. A matrix is an array of real numbers arranged in m rows by n columns. And in general, the dimensionality of the matrix is defined as the number of rows by the number of columns, so m times n. And note that you can think of vectors as a special case of matrices, where a column vector is basically a matrix where the number of columns is just one, and a row vector is just a 1 by k matrix where the number of rows is just one. Okay. It is also sometimes useful to think of a matrix as a being made up of a collection of row or column vectors. Okay, so kind of multiple column vectors stacked to next to each other, or multiple row vectors stacked on top of each other. Okay. We have a bunch of rules for how we can transform these matrices. The most basic one is matrix addition. So if we have two matrices A and B that have the same dimensions m by n, then the addition of those two matrices is just the elements added to each other. So the result is again an m by n matrix where each element is the sum of the individual elements in the original matrices. Similar to what we said with vectors. Oops. Let me just. The matrices A and B must have the same dimensionality, in which case they are conformable for addition. Next, we can also multiply a scalar times a matrix. This is called scalar multiplication. And if you multiply a scalar times a matrix, then each element is multiplied by that scalar, similar to the vector case that we talked about. Matrix multiplication is another important concept where we kind of have to go through the logic in a couple of times to kind of wrap your head around it. In general, if A is an m by k matrix and B is a k by n matrix, so the number of columns in A is equal to the number of rows in B, then their product C is equal to their product C will be an m by n matrix. And note here how as I said, the columns in A are equal to the rows in B, and the result will be an m by n matrix. This is a general pattern that you will see with matrix multiplication, where each element in C, so Cij, is equal to the sum of ai1 b1j plus ai2 plus b2j. So basically for our A, for Cij, so the ith row and jth column in our new matrix C, is a sum of the product of the A and B elements of the original matrix, where we ultimately take all the rows, or we go through, basically we keep the row in A constant, and we go through the first, second, and so on columns of A, and we keep the in our B matrix we keep the column constant at J, and we go through the first, second, and third, and so on row in our B matrix. So to kind of give you a better idea of how this looks like, suppose we have two matrices, A, B, C, D, E, F times A, B, C, D. And note, first we have to check whether the dimensions match up. So this is a 3 by 2. This is a 2 by 2. So the number of columns here is equal to the number of rows in the second matrix. So we can multiply them. And the result will then be a 3 by 2 matrix. Okay. And now the first column and the first row and first column element of that new matrix of that product will be, now we go in the first matrix, we go through the first row A, the first element A, times the first element in the first column of B of the second matrix A. So A times A plus B, this second column, first row, times C, second row first column. Okay, so this is A times A plus B times C. If we look at the second column, first row, we go through the first row of the first matrix, so A and B are the two elements, and we go through the second column of the second matrix, so B and D are the elements, and then it's A times B plus B times D. Similarly, if we have here CA plus DC, that is the second row, C and D, and the first column, A and C, and so on. Okay, so in the math Prefresher, there are a couple of examples, and I would encourage you to kind of go through that, make sure that you kind of get the idea of the underlying logic. And I kind of did this implicitly. Note that the number of columns of the first matrix must always be equal to the number of rows of the second matrix, in which case these two matrices are conformable for multiplication. Okay, the size of the matrices, including the resulting product, must then be equal to the number of rows in the first column and the number of columns in the second, the number of rows in the first matrix and the number of columns in the second matrix. Okay, and I realized that I didn't, or the pointer here didn't work. So I'm just going to go through this one more time. Through the logic, what I meant. So for example, if we here look at the second row, second column, or let's do the last element. This is the third row, second column of the resulting matrix. This is the way we get to this result is we look at the third row of the first matrix, so E and F, and the second column of the second matrix, so B and D. So we multiply E times B plus F times D, and that's this equation. For example, let's look at this one. The second row, first column. We go in the first matrix to the second row, in the second matrix through the first column. So it's C times A plus D times C, and that's what we see here. So that's the underlying logic. I went through it before, but my pointer didn't work properly. So I hope it is clear enough. If not, we can go through some examples in the Q&A session. There are a couple of important laws of matrix algebra. The first is the associative law, so A plus B plus, in parentheses, plus C is equal to A plus parentheses B plus C, so we can shift parentheses and matrix addition around. Same with multiplication and parentheses. We also can switch around for addition, we can switch around the order, and we can distribute similar to what you know from regular algebra. But what is most important is that the order matters in matrix multiplication. So A times B is not equal to B times A. Another important topic in matrix algebra is the transpose of a matrix. In general, the transpose of the matrix m by n, the m by n matrix A is the n by m matrix AT, also sometimes written as A prime, which is ultimately just obtained by interchanging the rows and columns of A. So we're just flipping around the dimensions. So in other words, if we have the matrix A that looks like this, the transpose of that matrix is just flipping around the rows and columns. So the first row here becomes the first column, and so on. There are a couple of rules that apply for transposed matrices. If we have the transpose of a sum of two matrices, that's equal to the sum of the transposed matrices. If we take the transpose twice, we get the original matrix. A scalar times a matrix, and the transpose of that is equal to the scalar times the transpose. And importantly here, if we take the transpose of the product of two matrices, then that's equal to the transpose of the individual matrices, but we have to reverse the order. So AB transpose turns to B transpose A transpose. Another important concept is the rank of the matrix. The rank of the matrix describes the number of linearly independent row or column vectors in a matrix. So for any matrix A, the row rank, and for any matrix A, the row rank always equals the column rank, and we refer to this number as the rank of A, right? So, for example, now thinking back to what linear independence means for vectors, ultimately we kind of apply that logic for matrices. Here we have a 3 by 3 matrix of rank 3. So these three, all 3 rows or 3 columns are linearly independent. None of the rows is a linear combination of the other 2. Here we have also a 3 by 3 matrix, but the rank is 2, and this is because the if we look at this example, the third row of this matrix is a linear combination of the remaining 2 rows. So if we add the first row to the second row, that's the result of the third. The result is equal to the third row. So the third row can be described as a linear combination of the other 2 rows. So the rank is equal to 2. There are only 2 linearly independent rows or columns. The same argument holds, of course, for the columns, right? So if we add the first column to the second column, we end up with the not the first to the second. Whatever. In principle, the same. As soon as the linear combination of rows, or as soon as the rows are not linearly independent, then the rows are also not linearly independent. Okay. I just want to make sure. Okay. Okay. All right. Lastly, I'll stop here, and in the next short video, I'm going to talk about the inverse of a matrix.